Next we have Charles Taylor. I don't want to get the wrong Florida. University of Florida? Okay, University of Florida. He's going to talk about a title that was too complicated for me to remember between there and here.
Oh, I'm so disappointed.
Charles Taylor.
Thank you. Is this working okay? Where's the slide? How do we do the slides?
It's on the top on the right there.
Oh.
Sorry, man.
Oh, this.
There you go.
All right. It's a little bit confusing. I'm Charlie Taylor, Associate Director of what we now call Research Computing at the University of Florida. I've asked our systems architect, Craig Prescott, to my left here, to join me for the talk since he was instrumental in what we're about to present. Before I get started, I'd like to thank the sponsors and the organizers of this meeting. I think it's gone really, really well, and I'm really glad to be here. I've never been to Austin, and I really like it, so thank you. As much as I like coming here, it's always a little bit humbling to see these systems like Sequoia and Jaguar. We don't name our systems at the University of Florida, but if we did, I think it would be more like Dandelion and Kitten. We don't short stroke 15K drives. We buy 5.4K drives and try to figure out how to get user data on the reserved sectors. So it's a little bit different environment. By way of motivation, we started out with Lustre, I guess, what, 5 years ago? 5 years ago, probably, and it wasn't a smooth start. That's not necessarily Lustre's fault. We were a little bit wet behind the ears, and we got our hat handed to us initially. So we had a few, I guess we started out with what, 1.6.0 maybe. And we had some stability issues and that went on for a little bit too long. And essentially the end result of that, including some data loss at one point, was that we got a little bit of a black eye with our users. We solved those problems within about, I don't know, within a few months, and it's not like we were going down every day, but it took a while to get where we wanted to be. And as a result of that, when we started thinking about our next file system, we started thinking about highly available Lustre and how we could do that. Next slide. There we go. So, keeping in mind that we don't have the largest budgets in the world, not that Sequoia and Jaguar do either, but our design goals in thinking about how we were going to do this were we wanted to minimize the cost per terabyte, maximize availability. We wanted good performance within the cost constraints, obviously. To do that, we felt like we needed to avoid externally attached SAS or fiber channel JBOD units. Avoid external RAID controllers. These things add cost. We, of course, wanted to support both Ethernet and InfiniBand clients. As much as possible, we wanted to use standard components and open source software. We only have a few minutes, so I'm going to skip through some of these slides. I think the big question for us came in, obviously, without externally dual attached storage, how do we do failover? How can one system see the storage of another? And the answer to that was obviously SRP, which I don't think I need to describe for most of the people in this room. So again, we're going to go past that. Low latency, SCSI remote protocol. And the advantage of SRP for us is it allowed us to essentially expose the storage in one commodity storage chassis to another commodity storage chassis so that essentially host A could see the storage on host B without, again, having the externally attached storage. And I don't need to describe RAID 1 to anyone. So what this ends up looking like is a failover pair, if you will, in which each host in the pair has OSTs consisting of mirrors, and those mirrors consist of a local LUN and a remote LUN. So it looks something like this. Without SRP, host A simply has drives and host B simply has drives. We add SRP into the mix, and now host A can see host B's drives and vice versa. We divide those up into mirrors. In our configuration, a mirror is only going to be active on one node at a time, obviously, because we're going to mount the file system on it. In the event, what's a little bit unique about the situation is, unlike in the external shared storage scenario where when one host goes down, all of the storage is still available, in our scenario, when one host goes down, we also lose the LUNs from that remote host, which is okay because in the context, the second host can simply continue to run in the context of a degraded MD mirror. So to build this thing, we wanted, again, to maximize performance within the cost constraints, so and get the density up as high as we could. So we looked for a chassis that was suitable. We wanted as many drives in it as we could. We couldn't get the density, of some of the commercial systems that are available, but we found a Chinbro RM91250, holds 50 drives, 48 data drives. We use 2 drives for system disks, mirrored system disks. Supermicro motherboard, that was fairly important because it had enough PCIe slots for us with the required lanes. We used Intel 5620 processors. I have a little more to say about that in a minute. 24 gigabytes of RAM. 4 Adaptec 51245 controllers, which worked out nice because we had 48 data drives and we did 2 RAID 6 4+2 LUNs per controller. You'll notice we have 3 InfiniBand control adapters in each system too. We'll talk a little bit more about that in just a second. The RAID configuration, as I said, 51245 controllers, RAID 6 LUNs, about 7.6 terabytes per LUN, 2 LUNs per controller, 8 LUNs per OSS. So we end up with about 60 terabytes per OSS. To keep track of the LUNs, because it gets a little bit confusing when you've got LUNs coming in from remote systems, we wanted to be sure that we didn't make any mistakes, because obviously if we synced the wrong mirror, we were going to be losing users' data. So we decided to encapsulate our LUNs in LVs and label them in such a way that it was obvious which LUN was which. And we adopted a scheme where the LUNs were labeled by their host controller and then the volume number on that controller. And that way it's always obvious to us which LUN is which. So the mirror on the OSSs ends up looking like this, with a LUN, which is obviously from each of the hosts in the failover pair. So you can see we have an H1 C1 V0 and an H2 C1 V0. And then host 2 will have a similar pair, and we just adopted the standard, that the convention that the V0 LUNs would be on the lower numbered host in our setup, and the V1 LUNs would be on the higher numbered host. So again, you end up with something that looks like this for our overall configuration. We will put 4 OSTs per OSS, and remember that there's 8 LUNs per host. So there's 4 local LUNs and 4 remote LUNs, and out of those 8 LUNs, we make 4 OSTs. And for failover purposes and for the pacemaker and HA software, which we'll talk about in a minute, we labeled those using a little bit of a non-conventional naming scheme for the MDs, but it was, again, just to enable the keep track of it in the HA software. So again, this is another look essentially at the same thing, but it's a little bit harder to read, but it shows you what the chassis look like and what the setup actually look like. This is our attempt to display the software stack from both the local and remote side of the picture. So on the local side, of course, you have the disk drives, the adapter, the AAC RAID driver. And then we hit the SCSI mid layer and go on up through the LVM layer, the MD layer, LDISC FS, and then the OST essentially sits on top of that. On the remote side, we of course start with the InfiniBand adapter, the MLX4 driver, OFED core, SRP target software, and the SCST shim layer, and then we hit the SCSI mid layer, and from that point on, the two sides are essentially indistinguishable, which is kind of nice. For the HA side, we use the familiar pacemaker and CoroSync. CoroSync providing the membership and messaging layer, and pacemaker providing the monitoring and management layer. I say familiar, it's familiar to some here. It wasn't familiar to us, so we had a little bit of a learning curve with that, but it went fairly well. Just a little bit about the CoroSync configuration, which I don't want to spend too much time on, except to say that we do use dual rings. One is a back-to-back Ethernet, and then the other one we use our IP over IB, SRP IB interface for the second ring. The pacemaker configuration was a little bit interesting and was fun to do. We took the standard Stoneth agent for APC smart PDUs, and we modified that to control not just one PDU but multiple PDUs, because each of our HA OSSs is plugged into 4 APC smart PDUs, which are then plugged into 4 UPSs. So if we were going to Stoneth, i.e. shoot the other node in the head, we had to be able to remove power from all 4 PDUs. And so we made those modifications to the Stoneth agent. We did a custom MD agent because the ones that were available in Heartbeat and Pacemaker didn't really meet our needs. And then used the stock file system agent. We set up the OSTs, as resource groups within Pacemaker, 1 resource group per OST. The resource group consisted of the MD and the file system, but not the LVs, and that's simply because Pacemaker would get very mad when one node went down and those LVs were not available anymore. Let's see. So what did the performance look like? Well, again, we had 4 PCIe RAID controllers per server, 2 RAID 6 4+1 LUNs per controller, 8 logical disks per server. And we could get about 400, and this is for large block sequential I/O, by the way. So 490 megabytes per logical disk, 650 megabytes per controller. We would have liked that per logical disk unit to scale perfectly, but the controller on RAID 6 gets a little bit parity bound. Note that we have 3 IB interfaces per server. The reason for that is that if you think about the setup in the HA environment, we have data coming in from the clients over IB, but then we're also mirroring over SRP, and we didn't want the mirror traffic, and we're going to be writing just as much data over the mirror as is coming in from the clients. So we didn't want the mirrored traffic to interfere with the client data. So we added in a second QDR interface and devoted it to the SRP mirror traffic, and they're in fact installed as separate fabrics. So we run OpenSM on each server in redundancy mode as well, and that's separate from the SM that runs on the wider fabric for the cluster. Let's see. Then we had a separate SDR interface to support IP over IB or Ethernet clients. We didn't want that traffic interfering with our higher performance IB clients. And let's see, again, I've already mentioned the SRP mirror traffic. So what does the performance end up looking like on this thing? From the client's perspective, we managed to get about 1.1 gigabytes per second for writes, 1.7 gigabytes per second for reads. Again, this is as seen by the clients. remember that everything that's coming in is being mirrored to the other host. So if you've got this happening across two hosts, what's really being written or managed by the system is 2.2 gigabytes per second. And that's 85% of the SGP survey numbers of about 2.6 gigabytes per second. And considering the number of layers of software we're going through there, we were pretty happy with that. The performance didn't come easy, and I'm going to let Craig say a few words about that. I think he did most of this work, and it was really really nice work. So I think he should have a chance to say something about it. You want to go over?
Talk for a couple minutes. The first thing we did after we got all this stuff together was bust out the Lustre I/O kit and run an SGPDD survey. As Charlie mentioned, we got about 650 megabytes per second per card to our two RAID 6 LUNs, and it was parity bound. But we were eager to see how things looked in Lustre with default settings for everything, and then apply tunings to kind of make up the ground that we knew we'd be missing. We were a bit disappointed to start off with how it looked through Lustre with no mirrors, so we were running in degraded mode with 4 OSTs per OSS, but we were running with a setup that the Lustre I/O size of a megabyte didn't match the max sectors KB on the block devices and on the MD layer, so it wasn't too surprising that there was some ground to be made up. First thing we realized that made kind of a big difference was that the alignment of our physical volumes actually offset things, so that every write we did, that would be naturally a full stripe, was actually straddling two RAID stripes. And we had to find some PV tools that allowed us to move the PV header onto a RAID stripe boundary. And so we did that and actually made a significant improvement. The next thing we did was to match up the MD max sectors KB and the RAID stripe size, and that actually netted us a small improvement as well. And then we tried to increase the max I/O size that our underlying LUNs could do. In the AAC RAID driver, that's controlled by a parameter called ACB size, and we weren't able to reach a 1 megabyte I/O with the ACB size parameter. We just couldn't. The value that would allow us to do it was there, but it didn't work for our cards. So we settled on a 512K max I/O and implemented that everywhere. Then we introduced the SRP mirroring, and we saw a benefit right away because MD rebalancing would allow you to read from both halves of the mirror and increase your read throughput. There was a small cost on the right side that the core responsible, I should say that we set the IRQ mask for our various devices in these OSS nodes so that a core that's local to the PCIe slot handles those interrupts. And the core that's responsible for the HCA that does our SRP mirror traffic tends to run out of cycles just a little bit before the rest of the cores does. So when the node is busy, we'll suffer a little bit during writes, but it's not a big effect. Charlie already described that we ended up achieving about 85% of the SGPDD survey result for the writes. For the reads, there was probably a little bit more we could do. Per OSS pair, we get 3.4 gigabytes per second. But we were happy, and we didn't want to spend more time tuning when we could put the system in place for our users. And I guess the only other thing I'd probably want to mention is some of the problems we encountered coming up with an open source IB SRP targets software that worked for us. We had to take a couple of shots at that. The first one we tried was the one that was included in the OFED stack we were using, and it wasn't stable for us. We ended up discovering the SCST project and rating their tip of their SVN tree to find something that worked just prior to their 2.0 releases. And we ended up choosing that, and that has worked out well. In Oddment, during our failover testing, when we were coming up with our ChorusSync agents, would be that if we allowed, if we would stone it one of our OSS nodes and bring it back, and then allow ChorusSync to reassemble our MDs from a dead stop. It's not something we do in production, since another node would have already taken over for the degraded OST. But we found that sometimes ChorusSync would choose the wrong half of the mirror to start from and sync from the wrong half. So we actually have a workaround in place now where we weren't able to reproduce this outside of ChorusSync, which is another oddment. But we have a workaround in place where we actually, when we are coming back up from a Stoneth event, we disable the LV that we know to be out of date. So we guarantee that the MD is safe. Let's see, performance was discussed. After we were in production for a little while, we ran into some workloads which were giving us a lot of trouble, and this turned out to have nothing to do with our SRP or anything like that. But we couldn't quite put our finger on it, but we were getting a lot of ChorusSync monitoring agents timing out, and OSTs unmounting and remounting as a result, and even some Stoneth events. And we couldn't quite track it down, and it turned out that we were probably the last people in this room to know about the zone allocator reclaim mode flag. And under certain workloads, that it was killing us, and we had to turn it off.
And sometimes under no workload at all.
Yeah. And we turned it off, and it made things perfectly stable under the same workloads. If we were going to do this again, and there's no guarantee we would, given current drive prices, since we actually have to buy more drives as a result. We save money in other places, but we have to buy extra drives for mirroring. Maybe now it wouldn't work out that way, to be cheaper than a conventional externally attached RAID. But things we'd look at if we were going to do it again would be something like an SSD cache, like similar to the Adaptec Max Cache feature, external journal device, RAID cards capable of larger than 512 KIOs, maybe faster processors, so we don't have a bottleneck on the SRP mirror traffic core. And we'd like to increase our storage efficiency. We were a bit gun shy, I guess, this is back in 2010 that we started this project, and larger than 8 terabyte LUNs were new to us at the time, and we didn't want to bite that off and find that it was going to cause us problems, since we figured that there was opportunity enough for us to experience trouble. And I think that's it.
Good job. All right.
You said you ran into problems with the OFED SRP. Did you feedback that experience to the OFED guys?
No, we did not. But we probably should have.
Yeah, grab me afterwards. I'll give you the contents.
Okay.
When you set up your solution, have you looked at DRBD? And if so, why have you chosen to proceed with your solution?
You want to say it?
Go ahead.
We were aware of DRBD. I guess it was a choice largely on comfort level, actually. I mean, we had experience with SRP in the past. We had some SRP target capable switches from Topspin years ago, and we used SRP in production for a long time, and we knew it worked well. DRBD was new to us, and we did a little research on it, but it did seem like there were we would probably run into issues things to learn in either case, but it was largely comfort choice.
We don't know a lot about DRBD. It looked to us like it was more used as a asynchronous replication tool for disaster recovery than for the kind of online synchronous higher performance solution that we were looking for. That's our understanding, but like I said, we don't have a lot of experience or knowledge of DRDB.
Thank you.
Dave Dillow in the back.
So, real quick question on the interrupt that problem you had with SRP. Was it on the initiator or the target side?
Target side.
Okay. And were you using the OFED initiator as well?
We were using the OFED initiator. Yeah.
Did you have any problems with connections kind of hanging up and going away?
We did, but those when those we had SRP login rejections, and we had when we were having the zone allocator problems, there were a variety of problems that we experienced, and some of them were SRP timeouts on the target side. But we haven't seen any since that's been repaired.
Okay, thanks.
All right, ladies and gentlemen, Charles Taylor, Greg Prescott.